This involves the pH unit. All right, we talked about water being amphiprotic. That means it acts as both an acid and a base. Well, this is called the autoionization of water. Auto is self, so the self-ionization of water. Again, like amphiprotic or amphoteric, water is not the only molecule that will do this. Okay, so over here, either can be the acid or the base form, but this one is the conjugate acid, and this one is the conjugate base. Now, because we did equilibrium in the last chapter, we know this is strictly a K. So what happens is this concentration, this would be the pure water, so it has a set value. So what we end up with is Kw. If Ka is acid and Kb is base, then Kw is water. Comes out to be the hydronium ion times the hydroxide ion, which is times 10 to the 14th. So this has the equations in it. This is a value you need to know. You will use it enough that you'll have it memorized, but it's easier if you just go ahead and memorize it. And this is real easy to remember because this is, you'll see that when we get to the pH scale. So just remember the Ka of water is 10 to the minus 14th. Okay, so here we take the water, and we know this value. So for a neutral solution, we know that the acid form equals the base form. So that means that if they're the same thing, you can substitute in the acid form for the base form and end up with two acid forms to give you the Kw. So we just rewrite it. And so here we're going to take the square root of both sides, and if we do that, we end up with, for a neutral solution, H3O plus is 1 times 10 to the minus 7. That also means, because we said that for a neutral solution they're equal, OH minus is the same. So then we're going to take the P function. Now, the P function is the negative log of whatever. It's like taking a percent. When you know that you're taking a percent, you're going to multiply it by 100. Okay, we did parts per million, parts per billion, and parts per trillion. It's no different, except the P function is the negative log function. Now, why do you use it? Because is it easier to say, I have a value of 1.0 times 10 to the minus 7th molar, or is it easier to say, I have a pH of 7? That's really why we do it, is we just take the negative log of whatever. Now, we could take your pH, you could take your P weight in grams, we could take the P function of anything we wanted. It is strictly a function. Now, the other thing you need to know that it is the base 10 log, not the natural log that we used before. So, if we take the Kw expression and we take the negative log of each side, okay, so we take the P function. So that gives us the negative log of the hydronium ion plus the negative log of the hydroxide ion is equal to the negative log of the Kw. Well, if the negative log is the P function, then that means it's pH plus POH is equal to pKw, which is 14. So if the pH is 6, then the POH has to be equal to 8 because they have to add to give to 14. Again, this is one of those things that you will use often enough that you're like, I got that. Okay? So that begs the question of, so how do we do this and what do we do with it? So first thing, we have to classify acids and bases. Okay? Well, if the H plus is less than 10 to the minus 7, while the OH minus is greater than 10 to the minus 7. The pH is greater than 7, while the POH is less than 7. If the pH is equal to 10 to the minus 7, while the POH is equal to 7, the pH is equal to 7, while the POH is equal to 7. Okay? So, if the hydronium ion concentration is greater than 10 to the minus 7, while the hydroxide ion concentration is less than 10 to the minus 7. The pH will be less than 7, while the POH is greater than 7. Basically, the P unit, if the smaller it is, the larger the concentration we see of the species. But they are inverses. So if you look at this little chart here, this is kind of cool. I took it from, I think, the other Pearson text. But we're going to start down here with a pH of 0, has a POH of 14. So the smaller the pH, the more concentrated it is in terms of the more acidic it is. And if it's greater than 7, then it's basic. So when we look at these species, it's kind of interesting because your gastric juices are down here. Your stomach makes hydrochloric acid, which is why when you throw up, you're ejecting concentrated acid and it'll burn your throat. So that's why it's more of a problem. Okay, as you go up, oranges, tomatoes, urine. Blood is actually slightly basic. Baking soda, seawater, household ammonia, 1 molar sodium hydroxide, we're talking Drano. And notice that at a pH of 14, which is very basic, the POH is 0. So the net effect of what this means is that when you have acids and conjugate bases, then you're going to have a difference. So for example, if it's strong up here, the conjugate is weak. And we have a statement for that shortly. Stronger the acid, the weaker the conjugate. So as the acid strength goes up, the conjugate strength gets much weaker. And we'll look at that in detail later. So here's what we look at. And these are all the relationships you need to know. You need to know that H plus times OH minus is equal to KW. KW is equal to 10 to the minus 14th. pH plus POH is equal to KW, which is 14. Ka times Kb is equal to Kw. More about that in a little bit. And then this is related. pKa plus pKb is equal to pKw. Okay? Typo there. So there's our pH scale. So let's go through here and calculate the pH of the following. So what we're going to do is we're going to take the negative log of 0.050. What that will give us is a pH of 1.30. So let's go to the next one. We're going to take the negative log of 0.012, and so we're going to get 1.92. Is that the pH? Nope. It's the POH. We know it's the POH because this is hydroxide. That means if we want to find the pH, we subtract that from 14. So our pH is 12.08, while our POH is 1.92. This again is acidic, so we end up with a negative 3.8. We can do that on paper. We can also do it in real life. They're kind of called superacids, but on paper it's way easier to achieve than in real life. This again is a hydroxide. So when we take the negative log, we don't get the pH, we get the POH, which is 0.77. Again, we subtract that from 14, and we get 13.23 is our pH. Again, this is an acid, so our pH is equal to 1.04. For this one's real easy because the pH is 1. Because if you'll notice, this is 10 to the minus 1. It's basically, when it's a 10, it's the exponent. So this one would have a POH of 2, because this would be 10 to the minus 2. So the pH would be equal to 12. This again is an acid, so the pH is equal to 3.40. So the trick to this is just identifying whether you're dealing with an acid or a base. So on this one, we're asked to calculate the pH of an aqueous nitric acid solution that has that volume and contains. So the first thing we need is we need the molarity. So we're going to start with 4,649 grams, divide it by your mass, which is 63.0129 grams per 1 mole. And I like to keep it simple, so 1 over 0.250 liters. Your grams cancel and you're left with moles per liter. So that gives you a molarity of 0.029511. So then you just take the negative log of that, 0.29511. So your pH is equal to 1.53. Now, guys, if you've noticed for pH, I'm keeping 2 places after the decimal. It just makes life a little bit easier. Now, here's another one. In a hospital laboratory, the pH of a bile sample is measured at 7.90. I'm going to skip to B real quick. Is this sample acidic or basic? If you guess basic, you're right. Because remember, basic is where the pH is greater than 7. So we're good there. Now let me show you a trick for this one. What is the hydronium ion concentration? Now there are a couple ways to do this. The hydronium ion concentration in times the hydroxide ion concentration is equal to Kw. That's one way. But watch how we did this. If we took the negative log of the hydronium ion concentration was equal to the pH, right? So if we move the negative, so if we have the log of H plus is equal to negative pH. Okay, what is the inverse of log? 10. So if we raise both, then the H plus concentration is going to be equal to 10 to the negative pH. So the hydroxide ion concentration will be 10 to the negative POH. So if we're looking over here at this, then we would say 10 to the negative 7.90, which when you put that in your calculator, you're going to get 1.2589 times 10 to the minus 8 is equal to the H plus concentration. Now, at a sure entertainment value or annoyance, whatever, is if you have 6.1, 10 to the negative 6.1. Let me double check this because right now I'm coming off an exam. 13, so that'd be right. That should give you a concentration of 7.94328 times 10 to the minus 7th, which is the hydroxide ion concentration. So if you look at it, it's slightly greater, so that actually makes sense that we would have that value there. Okay, so this is how we do pH from hydronium and hydroxide ion concentrations.